Okay. Now, for example, 1s correspond to an electron in the shell 1 in the s subshell. Now, 2p, you can see that is the address of the electron. 2p is an electron that is in the shell n equal to 2 and its subshell corresponding to L equal to 1. Now, how about the 3D? 3D correspond to the third shell, n equal to 3, and its subshell correspond to L equal to 2. L equal to 2. Or n equal to, yes, so n equal to 3 and L equal to 2 is a 3D address. Now, what does 1s2 means? When you have a number put as a superscript, that number is the number of electrons in that shell. So 1s2 means in the shell, in the first shell, in the s subshell, there are 2 electrons. You can see that address is now specified. What does 2p6 means? In the second shell, in the p subshell correspond to L equal to 1, there are 6 electrons. 2p6. Now, so it means that n equal to 2, there are 6 electrons in the p subshell. Now, this arrangement is known as the electron configuration. I'm sure most of you have done a chemistry course and you are familiar with the concept of electron configuration. Now, the placement of the electrons in a particular configuration is based on 2 principles, very important principles. The first principle is called the Aufbau principle, states that an electron will occupy the lowest possible energy available. Now, unlike in a class where students would come and sit as far away from the professor, is that right? You all do that. In an atom, that's not allowed. Electrons will occupy the lowest energy level, which are closer to the nucleus first, and then systematically fill the levels that are outside. That is the first principle. The second principle is called the Pauli's exclusion principle. That's a very important principle. What does it tell you? It tells you that no 2 electrons can have the same set of quantum numbers. Well, what does that mean? No 2 electrons can have the same set of quantum numbers. For example, let's consider the first subshell, n equal to 1, s subshell. N equal to 1, then L equal to 0. If L equal to 0, ML also equal to 0 because ML is plus or minus L. And MS can have either positive or negative value. So, in that S subshell, 1 electron can have this set of quantum numbers. N equal to 1, L equal to 0, ML equal to 0, and MS equal to 1/2. Now, the Pauli's exclusion principle says no other electron in the atom can have all these values the same. That means if there is a second electron in that shell, then its quantum numbers will be N equal to 1, L equal to 0, ML equal to 0, MS equal to negative 1/2. So you can have 2 electrons having different sets. You can see all these values are the same, but these are different. And you cannot have all these 4 values the same for any 2 electrons. That is what Pauli's exclusion principle says. No 2 electrons can have the same set of quantum numbers. Now, the energy level n equal to 1 can have only 2 electrons because of that particular principle, which correspond to n equal to 1, L equal to 0, ML equal to 0, and MS equal to either 1/2 or negative 1/2. Now, if you go to n equal to 2, the level n equal to 2, how many electrons can be there at n equal to 2? Can you locate that? Can you tell me how many electrons can there be at n equal to 2? Now look at this. N equal to 2 can have two L values, L equal to 0, L equal to 1. L equal to 0 is the S subshell. And S subshell can have L equal to 0, N equal to 2, L equal to 0, ML equal to 0, MS equal to plus or minus 1/2. That means there are two electrons in here. Alright? I'm writing it invisibly. In the S subshell for N equal to 2, there can be two electrons. If you now come to L equal to 1, L equal to 1 will correspond to ML. ML can have plus or minus 1 or 0. And you can see this will give you three combinations. And each of these three combinations can have MS either plus or minus. That means there are 6 electrons corresponding to L equal to 1 on the P subshell. So the S subshell can have 2 electrons and the P subshell can have 6 electrons, and therefore N equal to 2 can have how many electrons? 8 electrons. Alright, now I want you to figure out how many electrons can there be in the shell N equal to 3. You can see that's very simple now. So, you are now able to decide on the number of electrons per shell and in each subshell. In an S subshell there can only be 2 electrons. In a P subshell there can only be 6 electrons, and so on. Now similarly the level N equal to 2 can have 8 electrons, N equal to 318, and so on. Now aluminum with 13 electrons has the configuration. Look at this. First, the electrons will have to fill the first shell N equal to 1. And N equal to 1 has only one subshell, that is S. And that subshell can have 2 electrons. So 1s2 means 2 electrons in the first shell. And then you go to N equal to 2. That has S and P subshells. S subshell can have 2 electrons. P subshell can have 6 electrons. And once those S and P are filled, then you go to the third shell, N equal to 3. The S subshell there can have 2 electrons, and the remaining 1 electron will be in the P subshell. The total number of electrons will be now 2 plus 2, 4 plus 6, 10, 12, 13 electrons. So this is the electron configuration of aluminum. Nickel with 28 electrons has this configuration. You can actually now figure out the configuration of many more elements. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8, and so on. Well, here again is a description of the various energy shells, and of course each shell has its own subshells. Now, here's a picture of an orbital. What is an orbital? An orbital gives you the probability of finding an electron in a given space. So if you look at the S subshell, it will look like this. The density of the shading gives you the probability of finding an electron. If the density is greater, the probability is greater, and so on. The P subshell is like a dumbbell. The D subshell is a double dumbbell, and so on. Of course, the shaded area represents the probability of finding an electron in that shell. Alright, we talked about all this. Now, you remember I drew the energy level diagram in the case of the Bohr model, and I gave you the energy values for each, n equal to 1, n equal to 2, and so on. But if you now come and draw the energy level diagram for the quantum model, those levels are more complex because each level has subshells. So if you now draw the energy levels, you can see n equal to 1 has just one subshell, 1s. If you now go to n equal to 2, look at this, n equal to 2 has 2s and 2p. n equal to 3 has 3s, 3p and 3d. n equal to 4 can have 4s, 4p, 4d, 4f. And you can see they also overlap. Now, that's not going to be our concern in this lesson. That will be dealt with in a chemistry lesson. But what we are interested in is, because of these various subshells for each shell, the electron transitions can now have a lot more complex transitions. Now, you remember the picture I started with this lesson, the complex spectrum of helium? There are a lot more lines in there. Why? Because there are a lot more energy levels between which the transitions can take place. It is no longer a simple picture of the Bohr model. There are a lot more possibilities or combinations of possibilities for electron transfer. That's right. There are many more intermediate levels of energy, and there are thousands of possibilities of electronic transitions between these levels, and therefore you can have thousands more radiations than in the simple case of a hydrogen. Whereas Bohr model could only explain hydrogen atom with just one electron, the quantum model explains all observed phenomena for all elements. So we have actually found a good model of the atom. The quantum mechanical model clearly explains a lot of observed phenomena. So I would like you to appreciate the story of the atom models that we developed. It's been a great story that started many centuries ago and is still going on. The story is not finished yet because we still don't know what the building block of the universe is. If you know exactly what atoms are made of, then we should know what the building blocks are. If you know what the building blocks are, then we know a much more clear picture of what we are and where we come from. Do we know anything of that sort? I don't think we know. I don't think we have a clear picture. Well,